So I would like to introduce how to get a strong magnet. First, we have to define what a strong magnet means. As you can see, we define strong magnet as magnet with higher energy product. So if we are at point A, we will have relative applied field HA and the BA. The product of BA dot HA is energy product. So when we want to have a higher energy product, we can observe from its unit. In NKS system, the unit of energy product is joule per meter cubic. So in other words, it's meaning that it is energy per volume. If we want to have some magnet to do work, the higher energy product your magnet is, the fewer magnet you will need. In other words, you can do the same job with fewer magnet. There are some ways to have higher energy product. It either has higher remnants or higher coercivity and a better squareness. And in my presentation, I will focus on the coercivity. We focus on the microstructure and the relationship between coercivity. And there are two mechanisms that control the change of magnetization direction of domains. The two mechanisms are nucleation mechanism and domain warping mechanism. And in this picture, if we have an entire domain here and the magnetization direction toward this way, now we apply an opposite applied field toward this way. And when the applied field reaches nucleation field and opposite direction domain forms, and once that domain forms, it will propagate to the entire particles. So in nucleation domain, the most important field is nucleation field. It is a threshold. Once it is passed, and the entire material will change its magnetization direction. So if we want to increase our coercivity in nucleation mechanism, we want to increase our nucleation field. And researchers have found that as your particle size decreases, the nucleation field will increase. So one way to increase your magnet is to have finer structure. And second mechanism is pinning mechanism, just like nucleation mechanism. There is also a nucleation field, but when your applied field reaches nucleation field, your material the opposite domain won't propagate immediately. You have to further increase your applied field to propagation field. And once it reaches propagation field, the opposite domain propagates to the entire material. So in pinning mechanism, we want to focus on the propagation field. And researchers found that you can use additives to binding the domain wall from motion. So we can use additives to have higher coercivity. Now I would like to use a brief experiment to show the notion I mentioned before. In this experiment, we use two-phase magnet. The one phase is ferrite phase. It is a soft magnet which provides high remnants. And the second phase is neo phase. And it provides good coercivity. So we can combine both of them to have higher energy product. And we also dope titanium to have higher performance. As you can see in this picture, as with doping titanium, the grain size becomes much smaller. And with smaller grain size, we will have higher coercivity. That is one way to enhance your coercivity in the nucleation mechanism. And the other way is in this picture. You can see as we make our soft magnet become smaller. And once it becomes smaller, we will have higher coercivity. And when it reaches the size of domain wall width of hard magnet, it will have strong pinning effect on the domain wall. So it is an increasing way in coercivity in domain wall pinning mechanism. To sum up, I would like to introduce a procedure to enhance your magnet. First, you have to find the most dominant mechanism controlling your coercivity. And once you found that dominant mechanism, you can find ways to enhance your mechanism according to the controlling mechanism. And since China have recently limited the explosion of rare earth magnet, so we need to find an alternative approach to the rare earth magnet. That is the new magnet.
Back to 1972, Professor Takahashi found that the change of saturation magnetization with pressure of nitrogen during deposition. The result shows that the highest saturation magnetization as a specific condition, which is larger than that of bulk iron and cobalt iron alloy. They also attribute it to the appearance of alpha-double complex in this system. On the left-hand side, there is a general way to obtain alpha-double complex phase. First, pure iron is nitrated, and then the system is quenched to low temperature. Finally, martensite is tempered to obtain the alpha-double complex. It is worth to notice that martensite and alpha-double complex is the semi-stable phase, so it is not shown on the best diagram representing the thermodynamically equivalent of the system. In the following three slides, I will introduce the phases involved. In step one, austenite is obtained. The austenite has an FCC iron arrangement with nitrogen occupying 1/10 of octahedral rendered. And in step two, martensite is quenched. Martensite is obtained. During the quench, iron arrangement changed from FCC to BCC. However, nitrogen has no time to move from interstices. As a consequence, where the hole is occupied, ions are pushed apart in the spin direction. In step three, alpha-double complex is obtained. Basically, alpha-double complex is a BCP structure composed of a BCC unit cell. And ions are in three different types of crystallographic sites as designated as 1, 2, and 3. Iron in different sites may have different magnetic moment as Venn theory calculation. Here, the result shows that ordering of nitrogen affects the saturation magnetization. The higher the degree of nitrogen ordering is higher, the larger saturation magnetization will be obtained. In this size, determination of crystal and isotropy constant is demonstrated by the experimental result, curve and formula shown here. We can extract crystal and isotropy constant from there, and the results show that an isotropy constant is vastly independent of film thickness. Here, because as the figure shows, because of the nature of metastable alpha double quantum decompose at a temperature above 300 degrees Celsius. To improve the thermal stability, one dose the third element such as titanium to form titanium nitride, which stabilizes the alpha double complex up to 700 degrees Celsius. Just 3 months ago, there's a breaking news reporting about this material. The groups can that the powder they prepare have outstanding characteristics such as high purity, and high saturation magnetization, and high energy product. However, to be a substitute of permanent magnets, there is still some difficulties. There is still some difficulties. Mass production and reproduction of defect and variation, and improvement of low porosity and some solid